Welcome back everyone, Houston Math Prep here. We are going to do some integrals containing exponential functions in this video, practicing some U substitutions involving exponentials. We've got 5 examples we're going to work through in this video. We've got them shown here. So if you want to skip to a particular example and just see a couple of these, otherwise you can just work along with us. For our first one here, we have the integral of e to the x over 1 plus e to the x dx. And we don't have a quotient rule for integrals, so we have to figure out how to do this using U substitution. And one thing we might want to check when we have a fraction, you might go ahead and say, well, does it work for me to let U equal the entire denominator? And in this case, it actually does. So for this one, we would say U is equal to 1 plus e to the x. And the reason that works is because the derivative of 1 plus e to the x, well, the derivative of the 1 part is just 0. So the derivative of this is actually just e to the x, right? Technically, dx. And so we actually get that this 1 plus e to the x on the bottom, that's our u, and this e to the x dx here, that's du, and we get exactly a log rule. If I plug these in here, I get the integral of du over u, also known as 1 over u du, and this is a log rule, right? This is a natural log, so we say the natural log of u plus c, and we go ahead and replace our u in the ln, so we'll say natural log of the absolute value of u was 1 plus e to the x, so we'll say 1 plus e to the x plus c. And we'll make a little extra note here, 1 plus e to the x. So first of all, e to the x can't ever be negative. It's always above the axis if you graph y equals e to the x. And if we add 1, that's going to make it even more positive. So we don't really need the absolute value brackets here. We could go ahead and say ln of just the quantity 1 plus e to the x plus c, and that would be sufficient for this answer. Our second one here, we have the integral of e to the x over 1 plus e to the 2x dx. Now, especially after the last one, you might be thinking, well, what if I could just let u equal the bottom? What about 1 plus e to the 2x? And it turns out that's not going to work for us, because what is the derivative of that? The derivative of 1 is 0, but then the derivative of e to the 2x would be e to the 2x, chain rule would give us times 2, dx. And now e to the x dx is not just a constant multiple of 2e to the 2x dx. If this was just an e to the x, we'd have no problem. But we get a derivative that has an exponent of 2x. So we can't do this u substitution here. We need to choose something else. So what we'll actually need to do, think about choose something that has a derivative of e to the x. Let's just choose u to be e to the x. If I choose u equals e to the x, du is also e to the x, technically e to the x dx here. And that's exactly what I have on top, right? So this then becomes my du. But now it looks like my bottom isn't quite as simple as I had planned from the beginning, right? So if u is e to the x, I have, what do I have? 1 plus e to the 2x. The way we want to see e to the 2x, e to the 2x is really e to the x all squared. Properties of exponents says I can multiply the 2 and the x, and that would give me 2x. So if this is e to the x squared, this is actually u squared, according to the fact that we chose u to be e to the x. So our integral in terms of u, we have du on the top, but now we actually have 1 plus u squared on the bottom. And when you look at this, this is not a log rule, right? This is actually the rule for inverse tangent, if you recall that. So this is actually the inverse tangent of u plus a constant. And let's go ahead and replace our u back in terms of x. So u is e to the x. We'll go ahead and say this integral gives us the inverse tangent of e to the x plus c. For our next one here, integral of e to the square root x over square root x. It sure does look to me with a square root x here and a square root x here that u equals square root x is probably a good bet one way or the other, right? We'll just have to sort of see how this unfolds. So if u is equal to square root x, I'm going to go ahead and make a note that, remember, this is x to the 1/2, right? So when we're finding du, if it helps you to think of it as x to the 1/2, do that. So that would be 1/2 x to the negative 1/2 if we use the power rule for derivatives. Don't forget your dx. And now think about what this really says, right? This is really like 1 over 2, and then this is a square root x in the denominator, so we say square root x there, dx. So du is 1 over 2 root x dx. All right, so let's look back at our problem and see what we have. So e to the square root x, I think this is u here, so this is going to be e to the u. And now look at what we have here. This is really close to, we could think of this as the dx on top. That's really close to what we have left, right? We have dx over square root x. But we're off by a factor of 2 here. I have a 2 in the denominator. So let's write this down. We have du is equal to dx over 2 square root x. How do I get this to look exactly like what I have? I would need to multiply both sides by 2 because I want to reduce the 2 there, right? So we would actually get 2 du is equal to dx over just plain square root x, no more 2 in the bottom anymore. So this part here, dx over square root x, is actually going to be 2 du. So let's go ahead and replace all that. I'll go ahead and bump my constant multiple 2 out front. So we'll get 2 integral of e to the u du. And this is easy, right? Just an exponential rule. Antiderivative of e to the u is e to the u, so we'll get 2e to the u plus c. And now let's replace our u, right? U is square root x, so we'll go ahead and say 2e to the square root x plus c. When you look at this one, think about if you choose cosine of e to the x to be your u, the derivative of cosine something is negative sine of something, right? And I don't see a sine function anywhere to really deal with that. Another way to see this, I think, is that we don't have a chain rule for integrals, and that's what u sub helps us with. So maybe just picking the inside of some function only instead of the whole function itself might be a good choice. So let's choose u equals e to the x. That's a good choice because this thing out here is also the derivative of e to the x, right? So du then is e to the x dx. And this substitution works out nicely then, right? Cosine of e to the x becomes cosine of u. And e to the x dx is exactly what we have over here, right? So this part here just becomes du. So this integral just becomes the integral of cosine u du. No multiples whatsoever. So the antiderivative of cosine u is just sine of u plus our constant. Our antiderivative here, if we replace our e to the x, is going to be sine of e to the x plus c. Looking at our last example here, the integral of e to the x plus e to the negative x all over e to the x minus e to the negative x dx. This looks fancy, right? Let's say that we go in here and we just try to let u equal e to the x this time. That might help us take care of this and this, but the problem is, if we take the derivative of this, it's still not going to give me an exponential with negative x in the exponent. So these over here are still going to be a problem. A similar thing will happen if you choose e to the minus x. The derivative of that is still going to have negative x in the exponent, so then these would be a problem. It actually turns out if you let u equal the entire denominator here, u equals e to the x minus e to the negative x, then the derivative of that, so let's think about what we would get here. Derivative of e to the x is itself, minus the derivative of e to the negative x would be itself, but then the chain rule would give us what? It would give us multiply by this negative 1 derivative in here, and that would put a plus there, right? So we actually get du is equal to our numerator entirely. So this part down here is now u. This e to the x plus e to the negative x dx is actually exactly du based on that negative 1 coming out from the chain rule and giving us a different sign there. So we really get a log rule here. We get du over u for this one. That's going to be ln of the absolute value of u plus c. And then if we replace our u with what we started with, that'll give us ln of the absolute value of e to the x minus e to the negative x plus c. All right, everyone, hopefully some of these examples with u substitution and exponential functions have helped you out. Thanks for watching. We'll see you in the next video.